This is part 2 of lecture for chapter 2 on fluid statics. So we had looked at surface tension, capillary forces, and how they may or may not affect manometers, and had kind of determined that they don't affect manometers unless they're very thin tubes. Today I want to look at fluid statics mostly from a perspective of submerged flat objects. And then the next part we'll look at some curved surfaces in the same context. So there was our part 1, and now you're in part 2, and next you'll be in part 3. So let's look at some essential concepts here. Here's some tanks that we saw in Tuesday's lectures, and look at the pressure distributions on the bottom of the tank. All these pressures along the bottom are the same because the depth is the same everywhere along the bottom of the tank. Now, if we look at the side of the tank, the pressures are quite different. Large on the bottom and 0 on the top, or atmospheric more correctly. It feels atmospheric pressure, but we can call it 0 because all of this feels atmospheric pressure. The gauge pressure here is rho times G times H, or gamma H. Remember that rho G equals gamma. So pressure increases with depth. This pressure distribution is everywhere normal to the surface. So these are all normal vectors hitting the surfaces. So even though the pressure is given by a distribution along the depth, it's not just one value. We can come up with a resultant force vector that represents this pressure distribution. And that's what we want to do. So the magnitude of that vector is easy to get. It's simply the magnitude of the pressure at halfway down in this case, or the average depth of this object. So the center of this object, or the center of mass of this object, which is right here, because this object is a rectangular wall. I haven't drawn it very well. And its centroid would be right around here. So this depth gives the pressure, which if we take that pressure times an area, we will get the force on the wall. So the depth here of the centroid of the wall is 1/2 h. Therefore, the magnitude of the force, this resultant force, is the pressure part times the area. So remember, force equals pressure times area. So the location is a little more difficult. The location is not the same as the centroid of the wall. Instead, it's controlled by the centroid of the pressure distribution. So the centroid of this, in this case, this pressure triangle, where the centroid of this is where the resultant force will be. So for a triangle, the centroid of that pressure distribution is 1/3 up from the base. Sorry about that. Times H. Or 2/3 from the bottom, from the top, excuse me. So here it is. YR is 2/3 from the top. So let's look at a more complicated situation here, where we have a tank that's 10 feet deep, and in that tank there's a window or a gate, some wall part here that's 5 feet wide, 5 feet long, 10 feet wide, excuse me. This whole thing is 10 feet into the board here. If we twirled that out, we'd see the gate here, 5 by 10. There's the centroid. We have this x-coordinate system coming out. It's coming out of the board, but when we twirl it around, it comes this way. Either way, the y is the depth. So the pressure distribution for this one is also a triangular system. But now we have to notice that our actual object of interest really only starts right here. So this part of the diagram is not so important to us. It does add pressure because it makes the pressure here higher. The real shape of the pressure distribution that we're interested in looks more like this shaded trapezoid here. So we still want to know the magnitude of the force and the location of the force. The location is a little harder, but the magnitude still happens at the center of the object. So this one gives us the magnitude of FR. So magnitude, not the location, just the magnitude. The magnitude is given by the location is below the surface, 5 feet down. Here's the first 5 feet down. And then another 2.5 feet, which is 1/2 times the distance of the whole gate or window. So the total distance is 7.5 feet. So the resultant, the magnitude of the resultant force is 7.5 times rho g times area. Again, pressure times area equals force. Location is a little more complicated in this case. So in this case, we need to find the centroid of the pressure prism. And we know it's going to be a little bit lower than the center. Remember, for the triangle, it's 1/3 from the bottom and 2/3 from the top. And here it'll be not quite as far, but still there's lower pressure here than down here because there's more deeper water down here than here. So we use what's called the parallel axis theorem now, where we have our axis up here. We want to know how this may want to tend to twist or torque with respect to the x-axis, which is coming out at us. There's less pressure here, more pressure here, so it's going to want to turn this way. We're looking at this moment. And we use the parallel axis theorem. That's the moment of inertia calculation we use when we are offset from our main axis. We're all parallel to it. So we offset it by the centroid, y sub c, and then we take the moment of inertia of the geometric object. In this case, it's the object that we're looking at, so it's this rectangular shape of this wall right here. So this expression has yc plus the moment of inertia of this shape divided by yc times the area. Or in our terms here, if we look up in section 2.8 under the shapes, or if we remember from statics, maybe this is rather simple moment of inertia expression, 1/12 bh squared. We plug these in and we get a depth of 7.78. So as we said, a little bit below the centroid of this gate because there's more pressure below than above it. Notice that we did not have to do it with respect to the x-axis. So the x again is going into the board here. If we look at the x-axis, this trapezoid just repeats itself again and again and again all the way this way, so that it's same everywhere. So there's nothing trying to twirl it around the y-axis. There's no net moment going around this axis. It's symmetric in both sides, so there's no reason to compute the moment of inertia with respect to the x-axis. So that is the end of part 3, or part 2, so you can move on to part 3.